This morning we have some news about developments resulting from a space station science experiment that began more than 11 years ago. The Microencapsulation Electrostatic Processing System, or MEPS, was recently cited by International Space Station Chief Scientist Dr. Julie Robinson as number one on her list of the top 10 research results on the space station during its first 15 years in space. That was a space station science experiment that flew during Expedition 5. Well, today, the company that licensed the MEPS technology for use in cancer treatments is moving toward human clinical trials in the treatment of breast cancer. Joining us today is Dr. Dennis Morrison, a former JSC scientist who is the principal investigator on the MEPS. He is now a vice president with NuView Therapeutics, the company that I referred to. Start by telling us what it was you were looking to achieve when you started the MEPS research on the station in 2002.
Sure, Pat. The tendency for therapy in cancer treatment now is to go to what's called focal therapy, to try to put a focus on the tumor itself instead of having to expose the body to all the treatment therapies. So for radiation, it's a matter of focusing the radiation. For chemotherapy, it's techniques to be able to deliver the chemotherapy drugs directly into the tumor instead of having to give so much all systemically. Our approach to this was to make liquid-filled microballoons. These are like a children's water balloon full of anti-cancer drug and a contrast agent so that you can actually visualize them in real time as they're being deposited in the tumor. And then the outside skin, rather than being a rubber component, is made of biocompatible polymers that lets the drug slowly be released or slowly disintegrates over time so it disappears after a while.
A release system.
Exactly. So the approach was to make these unique microballoons in precisely the right kind of quality conditions. The difficulty is that the way we elected to make them, the different liquids, 3 different liquids, are different densities. So on Earth, they stratify into layers. As a result, it's hard to get them to come together to form little microballoons and form a skin in the right proportions. When we go to microgravity, surface tension takes over and all liquids go spherical. So it makes it much easier to put a sphere with another sphere and form a skin around the outside. And the trick is to be able to learn how to control those conditions so that eventually we can make them on Earth. And that was what the space experiments did. And in the space station, that was the definitive experiments when we did 8 experiments encapsulating 7 different kinds of drugs and a genetically engineered DNA.
We even have a picture that we can show of what that looks like.
Yes. On the left are microcapsules that were formed in space containing a photodynamic therapy drug. This is a drug that is activated after it's been absorbed by tumor cells. Mm-hmm. On the right is an example with the fluorescence showing that those microcapsules are full of the and evenly distributed of the anti-cancer drug contained inside.
Now, it's one thing to be able to make that in space. I guess the next step is how do you make it on Earth and make enough of it so that it can be useful?
Yes, and the trick is we had to learn how to control the conditions to bring these different liquids phases into interaction where they spontaneously would form the capsule. And the microgravity experiments with a variety of different conditions and real-time video of the capsules being formed in the MEPS device gave us the information to be able to develop a system called the pulse flow microcapsule system that we use on the ground now today, and we no longer have to go to space in order to be able to make the capsules with the right proportions of content and in large quantities.
Enough so that you can do experiments and find out just how they work.
That's true, and that led us to the capabilities to be able to explore several different applications for commercial use, and we did studies with the microcapsules that were made and now made on the ground to be able to treat human prostate and human lung tumors in animals to define the dose, the quantity, and the sequence of how often you need to give these capsules because they actually act as a sustained release form, releasing the drug over a period of 10 to 12 days.
You brought us a little clip of animation that shows us what this looks like when you give the drug.
Yes, that's correct. Let me suggest that there's 2 steps to this with the animation. This is the imitation of a growing tumor with the small deposits. Those is 1/20th of 1 drop of microcapsules being deposited in a tumor. And when it's exposed to near-infrared radiation, light, then the drug is activated, which kills the tumor. And that particular technology is such those drugs are absorbed only by the tumor cells, not by the normal cells. And the drug is totally inactive until the near-infrared light reaches them. Now, we got into that because we were studying the use of near-infrared light to stimulate bone cell and stimulate wound healing for astronaut use in a station. And that kind of a device was developed here. I have an example. This was developed for NASA under a Small Business Innovative Research grant years ago. And this light is set up with the near-infrared light, same wavelength as a laser pointer, but it penetrates deep into tissue. As you can see, this will actually penetrate in adequate quantities to be able to go 5 to 7 inches deep into tissue. So it's suitable to be able to use it for a handheld device like this, or be able to use it for fiber optics to deliver the light near the tumor and irradiate our microcapsules that have been deposited there.
You've gone from an experiment in space to learning how to make the same product on Earth in 1G. I understand that last week you were also in Washington, D.C., trying to get approval from the government agencies for the next step to try to test these products in human beings.
That's correct, yes. And we were with the Food and Drug Administration last week, and our initial step was we proposed to the FDA a plan to do the testing required to be able to use these microcapsules as a marker in breast biopsy sites when some breast tissue is removed, make a small deposit of a tiny quantity of our microcapsules. When you do that, we have a picture that sort of illustrates it in a tumor tissue. I think there's the next slide there.
That one?
Yes. In the upper left corner, I don't have a pointer, but in the upper left corner, there is a oblong tumor there, and there is a center that shows that there's microcapsules being deposited. That was 1/20th of one drop, and that was done in real time. You could see when the microcapsules actually come out of the fine gauge needle.
Wow. So
you can exactly position that. The use there is to have it as a reference marker for future tumor biopsies in case they're needed. You can see with ultrasound imaging, you can see where you took the first biopsy and carefully position where you're going to take the next biopsy, or as an aid to the surgeon just before he goes ahead and excises and removes that tumor. And that's the first step that we've approached the Food and Drug Administration about being able to use this in patients to treat as a diagnostic tool for human breast cancer. The next step, of course, is that the only difference between these marker microcapsules and a drug delivery one is we put the drug inside in the water content. So the next step is we're doing this, we'll be developing the same kind of test to show that the capsules are compatible with the body, they're safe, and they're effective for both imaging, but also effective as a delivery device to be able to treat the tumors. And our previous animal studies have shown that that's quite efficient in treating human lung and prostate tumors, and now this application will be for treating human breast tumors.
It'll be very, very exciting to see how that progresses. Thank you for bringing us up to date on this old station experiment.
Thank you, Pat. It's been exciting.
Dr. Dennis Morrison is the principal investigator of the MEPS experiment.